It's really, truly an honor to be able to share the Breakthrough Prize with my colleague Jean Malie from the University of Pennsylvania. But I would also like to point out at the beginning that there were actually several people who made crucial early contributions to this subject. And the field would not have developed in the way it had if it weren't for their important contributions. So I'd like to begin by publicly thanking those people. And so this initial work was about 10, 12 years ago. Over that 10, 12 years, the field has developed immensely. And today there are many groups all around the world working on this. And these many groups are the people who are going to be pushing forward to the next 10 years, for the new developments that I'd like to give you some flavor of what we think is going to happen. And so what topological insulators and topological phases of matter are about in general is what can you make with the matter that we have. And the building blocks of matter are actually pretty simple. You have electrons and protons and neutrons, and they're governed by the rules of quantum mechanics. So these are the laws of nature that were worked out in the early part of the 20th century. Now, there are branches of physics that seek to look on finer diracs, to look inside the proton and find more finer details. But for many purposes, that's not necessary. And Paul Dirac, one of the geniuses of the early 20th century, said it this way, that basically we have everything we need to know to understand much of physics, all of chemistry. There's just one problem, which is that the equations that you have to solve are too complicated. And now that's actually a big problem because complicated, when you have 10 to the 23rd particles, if you want to think of a quantum state of 10 to the 23rd particles, it's enormously complicated. It's so complicated, it's hopeless to even begin thinking about how much information is contained in this many particle wave function, okay? And so it's hopelessly complicated, but there's another amazing fact, which, and Philip Anderson said it this way, which is that more is different. And that when you have systems of many particles, simplicity can emerge out of the complicated behavior, okay? And what I'm going to be describing to you, topological phases, are an example of this emergent simplicity, and new organizing principles emerge at these different at this new level, which are in a sense are just as fundamental as the fundamental building blocks. Okay, and so this is the idea. And I want to talk about topological phases of matter, and let me just start with the simplest one. Okay, and the simplest one is just an ordinary insulator. So in an insulator, quantum mechanics tells us that electrons are basically snapped into place in the atoms. Okay, that's what quantum mechanics is. It's sort of like Legos. They snap in, and they can't. There's no play. They don't move around. And in an insulator, all the electrons are basically snapped into place, and they can't move anywhere. So there's a sense in which the insulating state is the most boring state. The electrons don't do anything. But there's one thing that you can do, which makes it a little bit more interesting, is you can actually add an electron. And if you add an electron, that electron can move around. Okay? It can conduct electricity. Okay? And so there's a sense in which that added electron can move around just like an electron can move around in empty space. It's like a particle that can move around in empty space. But there's another thing that you can do in an insulator, which is you can remove an electron. Okay? And so this missing electron, we call this a hole, it can move around too. It's like a particle. Okay? So this insulator has a new kind of particle that wasn't there in the original building blocks. It's a new kind of particle that emerges out of the collective behavior of all of the electrons, okay? And so there's something fundamental about this insulator, which it has these elementary excitations, which are electrons with a charge E and holes with a charge minus E. Or maybe the other way around, I guess. But actually, this is actually kind of like the empty space, the vacuum. Okay, so the vacuum has electrons can move around, But actually, if one of the lessons that Dirac taught us in quantum theory is that actually there are sort of holes in the vacuum too, okay? And those holes are called the antiparticles of the electron, called the positron. So there's a sense in which the electron and the positron are really just like the electron and hole in an insulator. And so what this means is that the insulator is sort of like a model vacuum, okay, a model empty space. But the thing that this does is it makes it so that you have much more control over the properties of an insulator than you do of empty space. There are many more knobs. You can change the composition of what you're making the matter out of. You can change where the atoms are. And so quantum matter allows you to design designer vacua, okay, designer, empty spaces, which have emergent properties which you have control over, okay? And I'm going to show you ones that have, electrons and holes, and then there are going to be ones that are even more interesting than that. But you might think that if you had electrons and holes and you knew how to control them, you might think that would be kind of useful. A material that it's easy to add electrons and holes to is called a semiconductor. Okay, and of course, one of the great triumphs of the 20th century was mastering how you understand and control the behavior of electrons in semiconductors. And we were a little bit lucky about this. It turns out that the quantum theory of electrons in a semiconductor, what you can get away with is you can get away with just thinking about one electron at a time. Okay, and that's much simpler than having to deal with all 10 to the 23rd at once. And this theory, based on single particle quantum mechanics, is an amazingly good theory for describing the physics of insulators and semiconductors. Okay, and actually Berkeley here was one of the places where this theory was developed. This is Marvin Cohen's band structure of silicon, and don't worry about all the details here. But I just want you to see that we understand these materials in great detail. Okay, and that detailed understanding allows us to harness these materials for all of the modern electronics that you have in your pocket today. Okay, and so where we're trying to go with this is I'm going to show you that there are new kinds of materials that you can have that have different kinds of emergent vacua, different versions of electrons and holes. Okay, and the challenge for the coming decade and beyond is going to be to do for those materials what we did for silicon. Okay, where of course it took many years to perfect the technology of making useful things out of silicon. We're at the very early stages with these new kinds of materials. Okay, and to give you a little flavor about what these new kinds of materials are, let me start with another insulator. Okay, and this insulator is a one-dimensional insulator, by which I mean that it's called a polymer. It's a chain of atoms, and it's actually a chain of carbon atoms with hydrogen atoms attached. It's called polyacetylene. Now, polyacetylene is a semiconductor, which means that it's an insulator that it's easy to add electrons to. So you can add an electron to polyacetylene, and then it can move around. But an interesting thing happens when you add an electron to polyacetylene. It splits in half. Okay? And so what happens is it splits in half, and this charge E over 2, it's exactly a charge E over 2, it can move around, kind of the same way that the hole was able to move around in the picture I showed you before. This is a particle that's just as good a particle as an electron or a hole. Okay? And of course, it wasn't in the original building blocks. It's something that emerged out of this structure. Now, you can ask the question, how could this possibly be? It's impossible to cut an electron in half. Electrons are indivisible particles. But somehow in this material, we were able to get it to split in half. How can that be? Well, what happened here is that this charge E over 2 is sitting on the boundary between two distinct topological insulators. Okay? Now, if you think about polyacetylene, what's happening here is it's actually a sort of alternating strong and weak bonds. So these double lines are like double bonds, and the single lines are single bonds. Okay? And when you do that, there's two ways you can do it. You can either go strong, strong, or you can go weak, strong, weak. And if you have, and so I can call those the A and the B phases. And I would like to argue that those two insulators are distinct, and if you have the boundary between them, then something impossible happens on that boundary. Okay? And so this is the essence of what topological insulators are about. It's about splitting the indivisible. Impossible things happen on the boundaries between topological insulators. Now, this polyacetylene is a simple example of this, but there are now many, many more. Okay? And another example is what happens if you try to split a one-dimensional electrical conductor. Now, so I can imagine a one-dimensional electrical conductor. If I imagine adding lots of electrons to this, they can try to move around. But if you're in a one-dimensional hallway, okay, and it's crowded full of people, you're constantly, it's hard to get where you're going because there are constantly people coming and going, you're bouncing off people. That's a hard problem. And that's actually a hard problem in electronics. That's how the electrons feel when you make very small structures. Now, it turns out that what one can do is design a kind of insulator that can split this one-dimensional conductor in half. Sort of like if you had a crowded highway, you'd make a divided highway with traffic going in one direction in one place and traffic going in the other direction in the other place. And so this kind of insulator is called a churn insulator. And what it does is it separates the traffic into opposite lanes. And this makes the traffic much more organized. And in fact, the conduction in these one-way edge states is in a sense perfect. And that allows the conductance of these edge states to be measured, to 1 part in a billion. Okay, and so these one-dimensional edge states, they're impossible by themselves. You can't have one just completely isolated. There has to be the other side. Okay, and so what this topological insulator is able to do is it's able to split this one-dimensional conductor into two pieces which are impossible by themselves. Okay, now so there are more versions of this, and so the three-dimensional topological insulators, and this is really one of the things that Gene and I figured out, happen if you take a two-dimensional electrical conductor. It can be split now into a three-dimensional topological insulator where you have now this impossible half of a two-dimensional conductor on the top and on the bottom. Okay, and this surface conductor on the 3D topological insulator, which is again sort of half of this two-dimensional conductor, it has a very specific property. Okay, and I don't want to tell you what this picture means. We call it a Dirac cone. You can see it's a cone, but it's a very specific property that these surface states have. And in fact, if you make a material that does this, and in fact, bismuth selenide is one of the best topological insulators. You can look at it, it looks like a rock, right? It's a piece you can imagine holding in your hand, okay? But what it is, it's a topological insulator, which means that it's an insulator on the interior. It doesn't conduct electricity on the inside, but on the surface, it's a surface conductor, okay? And it's a surface conductor with this kind of impossible surface state on it that can't exist in isolation. Okay, and by taking a fancy picture of this surface using angle-resolved photoemission spectroscopy, Zahid Hassan from Princeton was able to see this textbook perfect-looking Dirac cone on the surface. Okay, and so these are materials which are discovered, and I think Jean Malie is going to tell you this afternoon about all different kinds of materials that are like this that one can have. It turns out that since these materials were discovered, we've realized that they're much more common than we really than we first thought. And there's a whole industry of scientists who are now discovering new materials and related materials and ways of thinking about it. And so what I'd like to do, though, to try to look forward a little bit is I like to think about, well, what kinds of things can you do about this? And let's try to get to the essence of how it can be that we can do these impossible things on the boundaries between these topological states. And what it boils down to is quantum mechanics, a mysterious feature of quantum mechanics called entanglement. And so what quantum mechanics allows is it allows, if you have a system, you can imagine it's composed of two pieces. And in quantum mechanics, the two pieces together can be more than just the sum of the individual pieces. Okay? And in particular, the two pieces can be correlated with each other in a very deep sense. And we call them, in quantum mechanics, we call them entangled. And that's sort of what's happening in these topological materials. That's the reason why, if you cut it apart, that there has to be this impossible thing on the surface. And so one of the challenges that we have for the coming decade and beyond is learning how to use and control this quantum entanglement that occurs in these topological electronic phases. So we want to learn how to exploit it in the topological materials that we already have, and we have many of them. And we'd also like to discover new classes of topological materials which have richer patterns of quantum entanglement in them, and understand the things that we can do with them. Now, what might you be able to do if you could harness quantum entanglement? One of the things you might be able to do is make a quantum computer. Okay? Now, classical computers, they do operations on classical bits, the zeros and ones that you can combine together to make the digits of a binary number. Now, in quantum mechanics allows something more mysterious. It allows a quantum bit, which is 0 or 1, or in a sense, it can be both of them at the same time. Okay? Now, what this allows, if you have a string of n quantum bits, whereas a single classical bit you can encode a single binary digit number, if you have n qubits, then you can encode all of the n-digit binary numbers at once. Okay? And this fact allows a quantum computer, if you could make one, which is a device that does operations on qubits. A quantum computer could be much more powerful than a classical computer. And it's known that there are classes of problems that a quantum computer can solve much, much more quickly than a classical computer can. Okay? And so designing making a quantum computer is one of the grand challenges for the coming century. I'm not going to promise that we're going to have a quantum computer in 10 years. So this is, but there are many things to do along the road towards doing that. And there are many ideas for how you might make a quantum computer. You see, the problem is it's very hard. And the reason it's hard is that there's a fundamental difficulty with making a qubit, which is they're very fragile. The problem is if you have a qubit and you look at it, then the quantum information is destroyed. So if you look at a qubit, if you measure it, you kill it. Okay? And so the problem is how do you keep a quantum computer from accidentally measuring itself? Okay? And so that is the grand technological challenge. How do you keep that from happening? And so there are different approaches. One approach is if you have your qubit, just try to keep it very, very isolated from everything else so that nothing measures it. That's one approach. What I want to tell you about now is a different approach which takes advantage of a topological phase of matter like the one that I've been telling you about. And so the idea there, if this is a possible solution, one which we are working to try to make happen, is to split the qubit. So I told you that topological phases, they can do this thing. They can split individual objects into pieces and separate them. Well, there's a topological phase called a topological superconductor. I don't want to tell you exactly what that is here, but I'll tell you that the way we think about it is very closely related to the way we think about, topological insulators, like this polyacetylene picture that I told you. And so what this topological superconductor allows you to do is to take a qubit and split it in half. Okay, a qubit is this two-level system. You split it in half, and half of it lives at one end of a one-dimensional wire, and half of it lives at the other end. Okay? Now, the beauty of this is that the information that's stored in this qubit is not stored in any particular location. It's shared between these two objects, which are in two different places. And so that means that if you were to look at one of the ends, then it's impossible to measure the state of the qubit. The only way you can measure the state is if you bring the two things together and look at them at the same time. Okay? And what this means is that the quantum information that's stored in this qubit is topologically protected. It's immune from this accidental measurement. Okay, and so this is a possible way of protecting this quantum information. And if you could do this, then the grand idea is that you can then take these objects, which are at the end, if you can sort of braid them around each other, then you can do operations on the qubits, and then maybe you can make a kind of a quantum computer out of that. Now, so this is also a hard problem, but this is something where maybe there will be progress over the next 10 years. There's already been some progress. We now are pretty sure that these objects exist at the ends of these certain semiconductor quantum wires, these indium arsenide quantum wires, which are sitting with a superconductor. This little peak here that's at the end is evidence that you have this end state, which should be half of a qubit. Okay? What has not been demonstrated yet is that these end states actually can store quantum information. That is something which we still have to demonstrate. I'm hopeful that that's going to happen in the next 10 years. You know, one thing that has to happen for this field to progress is we have to perfect the materials, you know, the same way that we've perfected silicon technology to make, you know, and have very, very good, you know, control over how to grow those materials. We need to be able to do the same things with these new classes of materials. Okay, and so this is one of the great challenges for the coming decade. Now, let me just close by talking about another challenge for the coming decade, which is to, you know, sort of think outside the box about what other kinds of things might be possible. So one thing that I told you about is that you know, this theory of semiconductors and insulators that we have. We were lucky because it was so easy, because you could get it by thinking about one particle at a time. Okay. Now, but that means that there's a whole vast frontier out there of states that you can't think about that way, okay? And we know that there exist states, topological phases, that have much richer patterns of quantum entanglement, and they have exotic properties. Now, I don't want to explain to you what these words mean: fractional quantum numbers, non-abelian statistics. Let me just tell you that they're really cool. Okay, and we know that these can exist in certain circumstances. So the Laughlin state of the fractional quantum Hall effect is an example of that. And one of the challenges that we have is to sort of do for the fractional quantum Hall effect what we did with topological insulators, to bring it to classes of materials that you can make and study in the laboratory in a much more versatile way. And so there's a challenge to doing that. It's very hard. You see, the problem is that the many-body problem is much harder than the single particle problem. Now, we actually, there's much understanding that we've been developing over this, but the theoretical understanding of these strongly correlated topological phases that we have is based on sort of a sort of idealized description of the system based on effective field theories and idealized exactly solvable models. And the problem with these things is you sort of lose sight of the original electrons. And it's hard to make contact between these beautiful effective field theories and actual real materials where you can predict and do experiments. Okay, and that's the thing that band theory was able to do. It was able to make this contact between these two. And so I think a challenge for coming up in the next decade is going to be building a bridge between these two. How do we incorporate non-trivial entanglement into band theory? Okay, and so I think this is something where young theoretical physicists who are coming up are going to be the ones who make the great discoveries in this. How do you think about this many-body problem? There are ideas which are being developed. Density matrix normalization group, tensor network states, maybe machine learning. How do you incorporate these things in order to build a bridge between the sort of abstract effective field theory description of strongly correlated phases and actual real materials? Okay, and so let me just sort of conclude by making the point that knowing the building blocks and how they fit together, that's only part of the story, okay? You need to understand the organizing principles for how the matter operates. And just as an example, you know, I'm teaching classical mechanics to my students right now. I have freshman students. They're learning Newton's laws. And, you know, the Newton, you know, basically got it all in 1687 in the Principia. He did all of Newton's laws. But it was only later that it was realized that an organizing principle for understanding classical mechanics is to think about energy, okay? And energy is an organizing principle that, you know, that of course is very, very important. Now, you know, the foundations of quantum mechanics were laid down in the early part of the 20th century, but I think that today we are still uncovering the organizing principles for how to think about quantum matter. Okay, and so I think this is you know, a challenge for the coming decade. And so let me just then you know, just finish up by saying thank you to my mentors, my role models, my collaborators, students, and postdocs. I couldn't have done this without you. So thank you so much.
You were talking about states that emerge from more fundamental particles.
Yes.
Can those states, is there any hints that they can give us about the fundamental particles that we don't already understand?
I'm sorry, say
so if these quasi-particles can emerge out of more fundamental particles, is there some sense in which the fundamental particles could themselves be emergent?
Sure, of course, of course. I mean, so look, I mean, you know, so there's a branch of physics which seeks to dig deeper and deeper into, you know, smaller length scales, higher energies, and understanding what the ultimate fundamental building blocks are. Okay, and so starting with that deeper theory, then the electrons and protons could emerge. So for instance, you know, the proton, if you look deeper, it's actually made out of 3 quarks, okay? But there's a sense, what the emergent thing that happens is that those 3 quarks are so strongly stuck together, you know, it's impossible to pull them apart. And so that means that this particle, the proton, emerges from that deeper theory. So I would say that in that sense, the electron and the hole of a semiconductor are in a sense as fundamental as the electron and the positron.